Okay, great. And our next speaker is going to be Sebastian Carrasco Gaxiola. So take it away.
Okay. Thank you, everyone. It's so good to see you, everyone, and be with such stellar people. And I want to thank the committee to select my talk. So I'm excited to talk about my research, surveying chromospheric activity, and relative ages of K-dwarf stars. But first, I want to do a little dynamic. Who here studies M-dwarf stars? Raise your hand. Okay. Who studies F and G stars? Okay. Who studies K-dwarfs? Okay, perfect. Perfect, but I will tell you why also I'm studying these stars. So, why K-dwarfs? We know that the second most common type of stars in the star neighborhood. There is a diagram from the 10 parsec census of recons. So, K-dwarf stars are twice most common as G-dwarfs, but are way less than M-dwarfs in percentage, okay? So, the habitable zones are way smaller than G-dwarfs. In their planets, they might orbit closer to the habitable zone, but also they have less high energy radiance than M-stars, okay, M-dwarf stars. So, they may be the Goldilocks for like planets in habitability, okay? But next, I want to show you an histogram, exoplanet detections within 50 parsecs, where in the x-axis is the MG as a proxy of stellar types, and in orange, where the K-dwarfs rely. So answering also Bill question, there is a detection bias around K-dwarfs. Is this real? Is it just starting selection bias? But also, this is not the only. If I go to surveys to pull data of chromospheric activity of stuff, they also there's a bias on getting data for K-dwarfs. Okay, there are plenty of data for M-dwarfs, there are plenty of data of GNF, but not many for K-dwarfs. Okay, so my science question motivation is the percentage of K-dwarfs that are young, chromospheric active or inactive, and mature, and also using these systems to select the best targets to look for exoplanets or superstellar companions. So this is my outline. I want to talk the Rockstar survey, the survey we're running at Recons, my observation methodology. Then I want to show you results about lithium, H-alpha, calcium, bisonize, and make conclusions. Okay? So let's go ahead. So in Recons, we have two catalogs of stars, the Recons K stars and the Recons M stars. So the Rockstar catalog has around 4,450 stars, 4,500 stars. They're all primaries, while the M-star catalog, ROMSTAR, has around 3,300 stars. They're also all primaries. For each catalog, okay, these catalogs were made with astrometry of Gaia, Hipparcos, and Recons astrometry. So here my friend's team in Madison, they're doing posters about how they build this catalog and some data, some results for like white companions. So every catalog, every survey has also, we run in 4 different surveys. We run a survey using raw velocities, like blind search raw velocities, also blind search with speckle for companions, a white companion search, and a characterization survey. So I work in the Rockstar characterization survey, and I'm surveying this volume complete sample within 40 parsecs from the sun. And I have, we saw a total of around 2,200 stars. And I want to present you results of the stars with declination southern than 30 degrees. It's about 1,600 stars. What I want for these stars are chromospheric activity, relative ages, rotation velocity, fundamental properties, rotation periods, and space kinematics. This is my project. But now I want to present you about the first three stuff, chromospheric activity, relative ages, rotation velocity. So what can I look for getting these parameters? So we know that in the atmosphere of stars, like the sun, we have the corona, where you see activity in high energy stuff. Then you see the photosphere, you can see flares in the photosphere. Then you can see different lines in the chromosphere and look for activity, right? So I study the photosphere and the chromosphere, specifically the lithium line as a proxy for ages, and then the H-alpha and the calcium line, second line of the calcium triplet for chromospheric activity, okay? So I did my observations with the Chiron spectrograph at the 1.5 meter telescope in CTIO, running by SMARTS. So this is a high resolution spectrograph. It has an 80,000 resolution in a slicer mode. And it observes between a spectral range between 4,400 to like 8,800 angstroms. So now I will show you a chart diagram, a chart diagram of my sample. This is the 4450 stars, and I observed already 95% of them. So I'm going to present you results of 1545 stars. I will complete my sample in the next few months, probably by summer. So my methodology, this is examples of spectra. In the top panels are the lithium lines, and you see also I'm counting for a continuum. Then I have a sample in the middle and bottom panel of the H alpha. And I use both profiles for fitting absorption lines and integration by windows for emission lines. So also every spectra was visually inspected for if the continuum was correct, the signal to noise, any SP2, etc. So for measuring activity in the calcium line, I subtract the templates that I made, empirical templates, from the actual spectrum, and I measure the residual accumulated weight. And then, after having all the active stars, all the young stars, etc., I select inactive mature stars to create Visa-Nice standards that I use to measure Visa-Nice. So now I'm going to show you the results for these 4 features. I will show you plots where the x-axis is the Gaia color and the y-axis is the results of the parameters I measure. So for lithium, first we started with a sample of 600 K-Dwarf stars, which 500 of them are in the Rockstar catalog. And we found 25 stars with lithium detection. Here I'm showing them in gray circles, and also overplotted are stars from geomoving groups and benchmark field K-Dwarfs. Now, after studying another 1,000 stars adding to this, I found another 65 young stars. Okay, so it's a total of 90 stars with lithium detection. And also, the other ones are classified as mature because I don't see any lithium. And so all these stars are classified as young with an equivalent weight greater than 15 milliangstroms. Then for H alpha, I took the first study for the equatorial sample, and we had around 500 H alpha measurements. And you see here it's a distribution in the bottom of the line. Then I added 1,000 more stars, and I fitted a line, and this line will be all my H alpha quiescent level. Okay, so we investigate the region between the quiescent level in the top of the plot, where all the benchmark stars are, all the actives. So any star with a H alpha value elevated, it's what we call an H alpha active star. Now with the calcium, now I'm showing you in different colors, in different figures, H alpha active stars, young stars, and stars that are either young or active. And now I want to show you the residual equivalent weight of a bunch of mature stars. Okay? See, this in purple dots are all the mature stars. We see how some of them they rely close to the H alpha active and young. Okay, so we don't see any detection of lithium. We neither see any H alpha activity, but they have values that they have greater than the residual. So I want to call a really conservative threshold around minus 0.1. So all these stars have excess in the calcium line. Okay. In the left here, I'm showing examples of how the spectra of these stars look like. So we have stars with emission, okay, activity. Then we have stars with like some core refilling, okay, but they don't show any, in some cases, any lithium or HF activity. And then we see the boring normal K-Dwarf stars. Now next, about Visa-Nice, I mean, this is a work in progress, but I'm using the Visa-Nice standards to measure the empirical Visa-Nice. And the empirical Visa-Nice I use them with slow metallicity, slow rotators, etc. So we saw a bunch of slow rotators, okay? And the average error around slow rotators are 0.5 kilometers per second. This is a work in progress. I have a difficult relationship with my supercomputer, so it's hard. But yeah. So in conclusion, we have the 11% of stars in the southern neighborhood are K-Dwarf stars, but now we have a good picture of how many of them are active or young. Okay, so this is color code. In the left side, we have just a representation of stars in the southern neighborhood with the white dot is the sun. So we have that 2.5% of stars are young, okay? Then around 5% stars are H-alpha active. 2% stars are active and also young. 3% of them are mature and also have excess in the calcium line. But 87% of them are mature, so they might be easier to look for extreme ride velocities. So that's all for my part, and thank you for your attention. And I leave you with a pretty picture from my last run in Chile that looks like the main sequence. Thank you.
Great. So questions for Sebastian?
Hi, Park Lloyd, Eureka Scientific. Nice talk. I am curious about the stars that are active but not young. How confidently can you say that they're not young? Do you know? I guess, yeah, I'll leave it there. I'm curious about them.
So why they're active? I will repeat the question. Why are they active when they show signs of maturity? Yes. So there are different processes that excite the atoms in the atmospheres. The calcium line, the H-alpha line, they form at different heights, right? And they are also excited by different processes. The calcium line is excited by collision, but the H-alpha by absorption of the photons, right? So it's a work in progress. It's spooky, I will say, but it's only the things I can get with Chiron. Okay, I don't have data in Chiron. It doesn't go that blue to the correlations, but I'm working on getting data like synchronous observations with star spectrograph that goes more blue, and also Chiron to do a calibration. Yeah.
A moment. So I'll do an answer question then. I noticed in some of your figures, you have stars labeled as young and in like stellar populations, Tuck-Hor, Beta Pic, et cetera. But those also had some young K stars that were not in known populations. Have you looked to see, is there any evidence of populations around them that we didn't know about?
I don't know yet, but I have all the data for specific kinematics and also this data that can correlate with the motion. But yeah, that's the work in progress. I don't know if we'll find any new like moving groups.
Yeah.
Who knows? But yeah.
Any other questions for Sebastian? Not that let's thank Sebastian again.